My name is Debbie Wheeler, and on behalf of Advanced Kentucky, I'd like to go over some problem-solving techniques for you with you for the AP Environmental Science exam. So let's get started. Here's some of the things that we'll talk about today. Scientific notation, conversion factors you should know, multiplying and dividing in scientific notation, calculating percentages, dimensional analysis, and then we'll do some practice, of course. Scientific notation is a way to express numbers in the form of exponents as the product of a number, something between 1 and 10, and it's always raised to the power of 10. For example, 650,000 would be a hard number for us to manipulate without a calculator. So scientific notation is going to be a lot easier because 6.5 times 10 to the 5th is just a bit easier to manipulate. Here's another number that's very small. 0.000543. A much easier way to work with that number is 5.43 times 10 to the negative 4. Notice that when it's a small number and when we're moving the decimal point to the right, that number is negative. 10 to the negative 4 is our exponent. And when we're moving the decimal point to the left, 1, 2, 3, 4, 5, that exponent is going to be a positive number. Okay, so scientific notation is going to really help us since we can't have a calculator on this exam. Take a minute, stop this video, practice this, and then restart it when you're ready to see the answers. Okay, 2.9 times 10 to the 7th. So remember, we're moving this decimal point 1, 2, 3, 4, 5, 6, 7 places. That's how we come up with this. The same thing here. We're moving the decimal point this time to the right. 1, 2, 3, 4, 5. And it's 8 times 10 to the negative 5. This decimal just moves one place to the right. 2.3 times 10 to the negative 1. If you still need some more practice with this, there are lots of opportunities for you to do that. There's lots of practice sheets on the web. So if you still need some more practice, by all means, go and find some places that can help. Commonly used numbers. So these are numbers that you should, automatically think of. 1 million, 1 billion, and then of course 1,000. So a billion is always going to be 10 to the 9. A million is always going to be 10 to the 6th. You'll see these written a lot on word problems, so just be sure that you can easily manipulate them. Okay, once you know how to put numbers or take numbers into and out of scientific notation, the next task is being able to multiply those numbers. So when multiplying numbers with a base 10 exponent, multiply the first factors and then add the exponents. Let's look at an example. 3.1 times 10 to the 5th multiplied by 4.5 times 10 to the 5th. So we're going to multiply 3.1 and 4.5, and then we're going to add these two exponents. So 3.1 times 4.5 is 13.95, and that's times 10 to the 10th because we added the two exponents, 5 and 5. And then since really scientific notation is supposed to be a number between 1 and 10, we can move that decimal place over 1, and this is the same number, 1.5 times 10 to the 11th. Remember, we have to add another exponent when we move that decimal point over to the left. Okay, if you feel comfortable multiplying numbers, let's do a practice problem together. Do you know how many people are in Kentucky? There are 4 million, and remember, we're going to practice with our exponents. That's 4 times 10 to the 6th people. So let's look at a problem. If each person consumes approximately 20,000 gallons of water per year, how much water is being used in Kentucky each year? So we can set up that problem, take our 4 times 10 to the 6th people, multiply it by 2 times 10 to the 4 gallons per person per year, and that gives us 8 times 10 to the 10 gallons. So notice that when numbers are in scientific notation, it's so much easier to work with them. 4 times 2 is 8, and then we're adding these exponents, 6 and 4, to get 10. Okay, just a little fun fact, Kentuckians use approximately 50 gallons per day. All right, if you've mastered multiplying, and remember you can always get on the web and find some more sources for practice if you need it. When dividing numbers, exponents are subtracted and the numerator exponent minus the denominator exponent, okay? So 9 divided by 3, we're going to go ahead and do that part. And then these numbers, 5 minus 3, is how we get our exponents here taken care of. So 9 divided by 3 is 3, 5 minus 3 is 2, so this is 3 times 10 to the 2, okay? And that's a lot easier for us to work with than having those great big numbers out of scientific notation. So let's try one. Here is a problem that's going to require you to divide exponents. How much water does the average American use per day? So daily indoor water use in the U.S. is 21 billion gallons. Now, in order for you to be able to answer this question, you're going to need to know how many people are in the United States. Hopefully you know that. If not, you will now. There are about 300 million people, okay? And there is that million again. Remember, million is times 10 to the 6th. So 3 times 10 to the 6 people. And we can move the decimal point over. Oops. This should be 3 times 10 to the 8th. Okay. So 300 times 10 to the 6 is the same as 3 times 10 to the 8th people. All right. And now if we set this problem up, remember 21 billion times 10 to the 9. We're going to divide that by the number of people in the U.S., 3 times 10 to the 8th. And that's a nice, easy number to work with. 21 divided by 3 is 7. 9 minus 8 is 1. So it's 7 times 10 to the 1 gallons per person, or 70 gallons per person. And you may recall earlier we talked about in Kentucky we only use 50 gallons per person. So we're actually using less water than the average American. That's yay us. Okay, calculating percentages. When you're calculating percentages, remember it's always part over whole. Okay, so let's keep that in mind as we go. If you ate 2 pieces of an 8-piece pizza, let's see how you could determine what percentage you ate. So we'll start with 2 over 8, which we can reduce to 1 over 4, and that's of course 25%. Okay, so again, you probably have already done really simplistic problems like this. It's part over whole, and we can apply this to lots of different problems. For example, here's a situation. A fishery has declined from 15,000 individuals to 6,000. What % decrease is this? Okay, so this is important. What % decrease? So we want to first calculate how much that's changed. 15,000 minus 6,000 is a 9,000 fish change in the population. And again, there we go, part over whole. So that change is a 60% reduction in the population. And anytime you're doing these kinds of questions, these kinds of problems, always ask yourself, does this make sense? And 9,000 is greater than half of 15,000, so 60%, that makes sense. Okay, for general percent calculations, remember to divide the part by the whole. So here again, a power plant wastes 5,000 kilowatts of energy for every 12,000 kilowatts of energy produced. What is the percent wasted? There's our part, 5,000 over 12,000 equals 42%. Does that make sense? Yeah, 5,000 is a little less than 50% of 12,000. So that does make sense. Okay, now that we can putting numbers in scientific notation, we can manipulate them by multiplying or dividing those numbers. We can calculate percentages. Let's look at dimensional analysis, because that's really going to come in handy as we're doing math on this test. Okay, a couple of things to know about dimensional analysis. It's also known as the factor label method. it's a way of solving unit conversion problems. So you've probably done unit conversion, converting feet to meters or something of that nature. This is the same kind of thing. It uses 3 fundamental facts. Okay, you've got a conversion factor. Here's an example: 1 dozen equals 12 eggs. You set up a mathematical problem that uses 1 or more conversion factors to get the units you're interested in. So if we were trying to figure out how many eggs were in a dozen, of course we already know that, but 2 dozen eggs times our conversion factor, and you're always going to set it up so that your units cancel out, and that will allow us to do our calculation. So dozen eggs cancel out, that'll leave us in eggs. That was our original question. How many eggs are in 2 dozen? And then we just multiply 2 times 12, 2 times 12, divide that by 1, and that gives us 24 eggs. Okay. All right, a couple of basic things about the test. The numbers are probably going to be fairly simple. The AP folks know that you've got a limited time and you have 100 multiple choice questions and 4 essays. You got 90 minutes to do each one of those. 90 minutes for the multiple choice, 90 minutes for the 4 essays. So they're going to give you numbers that are relatively easy to manipulate. If you start getting numbers like 1.365, it's likely that you're doing something wrong. Remember to show all your work, even for simple stuff. It's terrible to lose points on something that you know how to do just because you didn't show your work. So don't let that happen to you. Always include units. For some questions, you will not earn points if you don't include units. So that's really important. And know some basic prefixes. Okay. Here's an example of what you should know. Know 1,000 grams are in a kilogram. 1,000 milligrams are in a gram. 1,000 meters are in a kilometer. 1,000 millimeters are in a meter. 100 centimeters are in a meter. And 1,000 milliliters in a liter. So that's not all inclusive, but those are definitely some basic ones you should know. Okay. All right, let's do a little bit of practice. So here's a problem that was given in 2005. Between 1950 and 2000, global meat production increased from 52 billion kilograms to 240 billion kilograms. Okay, so in 1950 it was 52 billion, and in 2000 it was 240 billion kilograms of meat being consumed. During this period, the global human population increased from 2.6 to 6 billion. And notice we've got billion in there, and so we want to keep our scientific notation in mind. That's going to really help us. The first part of this is they want us to calculate the per capita meat production in 1950 and in 2000. Okay, in 1950, as it said in the problem, 52 times 10 to the 9, remember that's our billion kilograms, and we're going to divide that by the number of people, 2.6, again, times 10 to the 9 billion, and look how nice that is. Those are definitely going to cancel out, so we're just dividing 52 by 2.6, and that gives us 20 kilograms per person. Okay, now let's calculate the rate for 2000. So there was 240 billion kilograms of meat consumed, and there were 6 billion people approximately. Again, 10 to the 9, 10 to the 9, those are going to cancel out. So it's going to be 240 divided by 6. Nice, easy number. That gives us 40 kilograms per person. All right, we have fulfilled part A. Part B says, use the values from part A to calculate the change in global per capita meat production during this 50-year period as a percentage of that 1950 value. Okay, so being able to use our percentage calculations is going to come in handy here. We'll start with the 2000 meat consumption value, and that was 40, and we're going to subtract the original. So we're coming up with our part over whole. Remember percentage, part over whole. We're going to, that's going to be 20, and then it's going to be 20 divided by the original 1950 value. Okay, so we're getting our 40 minus 20 is 20, and 20 was our difference there. We're going to divide it by what it was originally, and of course that's going to come out to be 100%. So the during that 50-year period, the change in global per capita meat production was 100%. Okay, it doubled essentially. These are really simple calculations, but be sure on the exam you show them so you get full credit. Okay, let's look at a different word problem. So this was a word problem from 2010. It says termites are social insects that are essential decomposers in tropical rainforest ecosystems. Termites may account for up to 95% of insect biomass in tropical rainforests. Termites consume vast amounts of dead and decomposing plant material thanks to the work of mutualistic, cellulose-digesting microorganisms that inhabit their guts. And I can't help but break this down a little bit. Remember that mutualistic means that they both benefit, and termites are not able to eat wood, cellulose, remember, is in the cell wall of plants, without the help of bacteria. And so bacteria are the microorganisms. And I'm a biologist, so I think it's interesting to think about how do those microorganisms get into the termites, because little baby termites are not born with them. And they are the parent termites have the microorganisms, and so the baby termites eat fecal matter from their parents, and that's how they end up with those microorganisms in their gut. Just something a little interesting about that process. Okay, in addition to their roles as important decomposers, termites digest plant materials and directly contribute to carbon dioxide and methane emissions into the atmosphere. It is likely that, like many insect species, termites and their symbionts may be sensitive to changes in their microclimate caused by global climate change, especially with regard to temperature and humidity. Okay, so they're probably going to ask me something about carbon dioxide or methane emissions, just based on this introduction. And anytime they give you a table, take a look at the table and try and draw some conclusions from it before you even begin to read. Okay, so this has relative humidity across the top and its temperature. And it does tell me at the beginning of this, the table above gives the rate of wood consumption by termites in milligrams per day per termite under various temperature and relative humidity conditions. So this is a rate of wood consumption. So I always think, well, what's the biggest number? What's the smallest number? The biggest number is 0.27. And so it looks like at 30 degrees Celsius and 90% humidity, that's when termites are really ramping up their consumption of wood. That's when they're most active. And the opposite would be, let's see, at 40 degrees C, termites are not, 40 degrees Celsius, termites are not consuming any wood at any of the humidities. Okay, so they really don't like 40 degrees Celsius. Okay, let's see what else they have to tell us. Under optimal conditions, the emission rate of methane by termites is approximately 70 kilograms of methane per year per 1,000 termites. Okay, and I don't have a pen so that I can write on the screen with this computer, but if I were sitting down taking the exam, I would be writing these numbers kind of off to the side so that I could think about what I might need later to do some of these problems. Okay. So our first question is, according to the data, what are the optimal temperature and relative humidity for termite activity? So check that out. We already read the table and noticed that 0.27 is the optimum. We didn't even really need to do any calculations here. So at 30 degrees, 90% humidity, that's when termites are doing the most wood consumption. That's when their rate of wood consumption is highest. So that was pretty easy. The second one, given a density of 4.5 times 10 to the 7 termites per hectare and optimal conditions, calculate the annual amount of methane emitted in kilograms by the termites inhabiting a 2,000 hectare tropical rainforest. Okay, so sorry, I thought I'd pull my face in so you could see me a little bit, but my computer doesn't necessarily want to cooperate with me, so I don't know if I'll be able to do that. Given a density of 4.5 times 10 to the 7 termites per hectare in optimal conditions, calculate the annual amount of methane emitted in kilograms by the termites in a 2,000 hectare tropical rainforest. So let's start with the size of the forest, and then when you start to write these down, you see, okay, I'm using dimensional analysis. I'm going to make sure my units cancel. And we want to be in amount of methane emitted. And they told us earlier that there is 70 kilograms of methane per year per 1,000 termites. And so I know how to use that conversion factor because I want my termites to cancel out. My hectares are also canceling out. And so I'm going to end up in kilograms of methane per year, which is exactly what the question asked for. So there's my answer, 630 times 10 to the 7 kilograms of methane per year. And that's all I had to do. Okay, for the next one, suppose the temperature increases to 35 degrees Celsius and the relative humidity decreases to 50%. Using the data provided, determine the amount of methane in kilograms that would be emitted by the termites in the 2,000 hectare tropical rainforest. Okay, so there's our question, and we want to look back at this table. And 35 degrees Celsius and 50% humidity, rate of wood consumption goes down to 0.09. So that's going to be important for me to remember, okay? And I had already done that earlier calculation. So 0.09 is what it's at. 35 degrees, 50%, that's my rate of wood consumption. Remember that optimal was 0.27, and I had already calculated previously how much methane is being produced at optimum temperatures, okay? I'm going to get that in a little bit easier number. I'm just moving the decimal point over 2, so it's 6.3 times 10 to the 9 instead of 630 times 10 to the 7. Remember, these are the exact same numbers. And so I'm going to put the new rate over the optimal and multiply that by the methane that's produced by the optimal rate. And that's really easy. 9 divided by 27 is just going to be 1/3. And so when I do this math, 6.3 times 1/3 is really easy. What's a third of 6.3? It's 2.1. And I've got this in scientific notation. I'm not messing with all of those zeros. Okay, so that's just a little sample, a few little strategies I think that can help you on the exam. I hope you found it helpful, and good luck on the exam.